Hello everyone, I am Sun Ji from Tsinghua University, and I will introduce our paper, The Learned Cardinality Estimation for Similarity Queries. Similarity search and join has been well studied for decades, but there are less papers focused on cardinality estimation for similarity queries. The cardinality for similarity search denotes the number of objects in dataset whose distances to a query queue are not greater than a distance threshold tall. And the cardinality for similarity join denotes the total number of pairs QP from query set and dataset whose distance is not greater than tall. For example, the photo on the left can search 20 similar images with small distances from the web, and the cardinality of the query should be 20. The word basketball on the right can search 9 similar meaning words from text, and the cardinality of the query should be 9. Although both the image and the word are prepared as a vector by using embedding method, we only focus on how to estimate the cardinality for vector and distance threshold in this paper. Before introducing our method, we first survey some existing works that could be used to solve our problem and why they cannot be qualified in the task. The histogram-based method is widely used in modern database management systems, and building a histogram needs to group a column into buckets according to the absolute values. However, the distance of different vectors in a dataset is relative to the query, and if the query changes, the distance changes as well. Therefore, it's no way to build the histogram according to the distance. And the sampling-based method perform well for cardinality estimation for exact queries on low-dimensional attributes, but a small amount of sample hardly represents the distribution of high-dimensional data because of the curse of dimensionality. Recently, the learning-based data model, like autoregressive, performs well on estimating cardinality of query on structured relational data, but it's hard to fit the continuous data in a sparse and high-dimensional data space. There are also some methods being proposed for similarity queries. The kernel density estimator selects samples randomly from datasets and builds a Gaussian model on each sample point. The cardinality of a query is the sum of densities of all samples close to the query, and the densities are given by the Gaussian model. However, the method also has zero tuple problem because it relies on sampling. The linear mixture model selects some centroids according to recent queries and build a linear function with regard of distances. And it estimates the cardinality of a query according to the output of linear functions. However, the linear function is less powerful to fit high-dimensional data. And the variational autoencoder-based method is a state-of-the-art method. It performs very well for cardinality estimation if the training query is enough. However, the accuracy of it increases a lot because the low dimensionality, because the low dimensional embedding the VIE produces is not distance-aware representation. The basic idea for solving cardinality estimation problem for similarity queries is using a modularized neural network. In this neural network, the key features like query vector, distance threshold, and data sample are input into different layers and transformed to a single representation. And we use another learned neural network to predict the cardinality according to the representation. All the layers in the neural network is learned from existing training queries and their true cardinalities. Although the accuracy of estimator cannot be improved a lot with only this model, but this model gives us the opportunity to put more advanced ideas in it to better solve the cardinality estimation problem. We have observed some opportunities according to these two facts. Firstly, vectors far from the query can be ignored. Secondly, the distances of two vectors can be expressed as a function of sum of distances on segments. For example, the Hamming distance of sigmod and sigkdd equals to the Hamming distance of sig and the Hamming distance of mod kdd. Other distance functions will be shown in next slides. The real-world datasets are clustered, and the points in the same cluster is close to each other. We take the fashion MNIST dataset as example, and the dataset can be clustered naturally according to the distance. For a given query, many clusters may contribute 0 to the cardinality, and we could find a way to pre-prune those clusters and reduce the difficulty of cardinality estimator. We put 4 different distance functions here to show that the distance of two vectors u and v can be expressed as the sum of distances of segments from u and v. For example, the L1 and L2 distance is the harmonic mean of distances of segments. The cosine distance of normalized vectors is the half of L2 distance. The angular distance is the angle of the cosine distance. The Hamming distance is the sum of Hamming distances of segments. According to our observations, we first group dataset into clusters, and then we build a local model on each cluster. A query can ask a local model for the cardinality of the cluster. By summing the results of all local models, we can get the cardinality of the query. For each local model, we first split each query vector into segments, and then send them to a convolutional neural network. Layers of networks progressively aggregate segments into a representation, ZQ. The reason why we do query segmentation can be explained by this simplified example. The U is a query. We could split it into 2 segments, U1 and U2. Accordingly, all vectors in dataset are also split into 2 segments. We show the distance of segments in the figure. The distribution indicates the data positions whose segments have specific distance from query segment. The function f is learned to fit the distance aware distribution. As for the distance distribution of complete datasets for query u, we need another function g combining the distribution of segments. In this example, the g is shuffle and the bit end. At last, we get the density easily from the distribution. Until now, we have improved the accuracy of cardinality estimation higher than the state-of-the-art significantly. However, we have to remember that a good cardinality estimator must be efficient. One issue of our method is that we have hundreds of local models. Although these models are lightweighted, the latency of evaluating them all is very high. In order to solve this, we add a global index model, which can prune most of the local models where clusters are far from the query. The global index model is also a neural network, which takes the query and threshold as inputs and outputs a binary vector. We also add the distance between query and all centroids of clusters as a feature, because the distances roughly represent how many data were close to the query in that cluster. When we train the global model, we use the cross entropy as loss function, because minimizing it can improve both recall and precision of the index model. We also add a penalty error in the loss function to avoid the index missing clusters with many data selected by the query. The penalty is the normalized cardinality on missing clusters. The implementation details is shown in the figure. The query embedding model is a convolutional neural network. The filter kernel F scans all segments, and the next layers progressively aggregate the segments by neural networks and the pooling layers. Because that large cardinality is hard to fit, our local models output the logarithm of cardinalities. So what if the query is a set of vectors? If we estimate each of them and sum them up, the efficiency would be very low. One promising solution to solve this is to learn a canonical representation for the query set. We adopt sum pooling to merge query embeddings. That's because the sum operator can be aware of query size and makes our join model be generalized to different number of query vectors. In this figure, each vector in query set is transformed to the representation by using the query embedding layer. And then we add all representations together and send the mediate vector into estimation module. According to the metrics produced by global model, different queries can be sent to different local models. In this way, we can reduce the time cost by at least 50%. In order to thoroughly test our methods, we adopt 6 datasets with different distance functions and dimensionalities. The BMS contains product entries. The ImageNet contains one-hot vectors of images pre-processed by HashNet. The GLOW 300 contains 300-dimension distributed representations of words. The YouTube dataset contains raw face images from YouTube web videos. Abanda and DBLP contains binary vectors transformed from publication titles. These are methods we test in our experiments. The line 1 to 5 are our cardinality estimation method for similarity search. Line 6 to 10 are baselines. The QES uses the convolutional neural network for query segmentation. The local plus adopts data segmentation but removing the global model. And it employs automatic hyperparameter selection for each local model. The global local MLP uses data segmentation, but without using the query segmentation. That is using MLP for query embedding. The global local convolutional neural network uses both query segmentation and data segmentation. The global local plus improves the global local convolutional neural network by using the hyperparameter tuning algorithm. In addition, the methods 2 to 4 use a penalty in global loss to avoid missing data segments with large cardinalities. The line 11 to 13 are methods for similarity join. The convolutional neural network-based join uses a sum pooling for combining all segmented query embeddings, but does not use data segmentation. The global local join does not perform query segmentation, but adopts data segmentation. The global local join plus uses both query and data segmentation. It also uses the same tuned hyperparameters as used by global local plus. We also use estimation method for a similarity search as baselines for join estimates. For given queries, we take 80% of them as training queries and the left are taken as test queries. For each query vector, we select 10 different thresholds, and the maximal selectivity is lower than 1%. That is accordance with real queries. For join queries, we train our model by using 1 to 11 vectors and test the model on larger query sets to show the generalization of our model. We deploy our experiment on a machine with Intel CPU and 128 GB memory. We select datasets BMS and Amanda as examples to show the accuracy of our method for kinetic estimation of similarity search. We can observe that learning-based method outperforms 1% sampling-based method because sampling suffers from zero-tuple problem. But 10% sampling method outperforms all other methods because it selects too many samples. Methods with query segmentation outperforms MLP because query segmentation can better capture the data distribution for similarity distances. Methods with global local framework is the best because data clustering and filtering reduce the difficulty of fitting distributions of local models. We also select BMS and Amana as examples to show the accuracy of our method for kinetic estimation of similarity join. We can have similar observations as previous slides. Note that bonding query vectors together can improve accuracy because more vectors make the distribution of kinetics in workload more smooth. This figure shows that our method can be effectively generalized to larger query sizes for similarity joins. We can observe that the error only slightly increases when query size increases by 3 times. For efficiency, we can observe that sampling method takes the most space because 1% sample is large. The QES model is the smallest because convolutional neural network is lightweighted and it has only one model. Our global local model is similar to the state-of-the-art method Cardinality, and they also have similar performances. Well, for kinetic estimation of similarity joins, we can observe that global local model with some pooling is the best in efficiency because we only need to compute the estimation layer once for our join query set. 10% sampling method is the slowest because we have to compute distances for each vector in join query set and each sample. In conclusion, we make following contributions. We propose a basic neural network model for kinetic estimation of similarity queries. We propose query segmentation and data segmentation to improve performance of model. We extend the model to support similarity joins. We conduct comprehensive experiments on real dataset. We also special thank to the National Nature Science Foundation of China, Beijing National Research Center for Information Science and Technology, Huawei Company, and TAL Education Group. Thank you all for listening.